Thank you, Abby. Welcome, everyone. I am extremely honored to have the opportunity today to present alongside my esteemed colleague Ryan, as well as Abby, in what is actually my first webinar under the Maxar umbrella. And I'm also excited to have the opportunity to talk to you about our topic today, and to focus in on kind of what it really means to bring the globe in 3D, this capability that I've spent the last 5 years of my life at Vricon helping to develop, really bring it into the larger fold here at Maxar. So jumping straight in, I think many of you who are on the call today will have probably seen the announcement that came out early in July about Vricon and Maxar officially coming together to become one company. So for those of you on the call who may not be familiar, Vricon, where I come from, was an organization that was set up as a joint venture back in 2015 between what at the time was Digital Globe and their partner Saab AB out of Sweden. And for the last 5 years, myself and our team at Vricon have been building up a capability that leveraged the best of the capability that Digital Globe brought to bear in terms of high resolution, accurate satellite imagery, alongside some really powerful technology that Saab brought to the table. We brought those two things together to build out a capability to go, quite simply, build the entire globe in 3D. The globe in 3D, when we first set out in 2015, was a concept that we put forward that would take cutting-edge computer vision and image processing algorithms and intellectual property that had been developed under the Saab umbrella for many, many years, and bring them together and pair them up with the largest commercial archive of high-resolution satellite imagery that's available. So Digital Globe, as I'm sure everybody on the call knows, had for over a decade been collecting massive quantities of commercial satellite imagery, pulling it down, and we, through the formation of this joint venture, were able to get access to that archive of high-resolution satellite imagery and pull it together with this really cutting-edge image processing technology. And we built out an organization that was laser focused on establishing a commercial production capability to build high-resolution 3D data at global scale. So our primary focus for the first 3 years of our existence was to build out this scalable capability to build 50-centimeter resolution, fully textured 3D data with absolute accuracy in a global context of better than 3 meters in all 3 dimensions, without using ground control points, a purely automated process with human QA and QC included in order to be 100% certain of the quality and accuracy of the product that we were putting out, but to create this as a commercial data product that could satisfy a broad range of different use cases, both on the kind of traditional government and defense markets, but also in the commercial marketplace as well. So we at Vricon spent the last 5 years kind of establishing and growing this capability, and as of July 1st of this year, we had the opportunity to be brought completely into the fold here at Maxar, and we couldn't be more excited about it. So the purpose of the webinar today is to really talk about a few key pieces of what that means, what the implication of that transition means for us as Vricon, for Maxar, and ultimately for the community and customers that are out in the marketplace. So we're gonna start off the the next section of this webinar with Ryan, who is going to spend a little bit of time talking about the foundation of what we have established at Vricon and are establishing now at Maxar from a data perspective, and how that can apply to a number of different use cases. And then as we get through that, and as Ryan works through those initial use cases, we'll jump back into some additional focus on what this means from an application standpoint, looking at some more of the cutting edge technology solutions that are being built on top of this content to satisfy specific customer use cases that are out there. And then I'm going to finish off by talking about what this means for the future, looking at some of the really exciting product developments in the larger Maxar portfolio and how they're going to impact this kind of core mission that is, I think, so important to everybody, both here on our team, but also hopefully to everybody who is listening today. So with that, Ryan, why don't I hand it to you? You can get us started.
Can you guys hear me? Yep.
There we go.
I appreciate that, Isaac. Hey, thank you guys. And I think Isaac summed it up really nicely, talking about the excitement we have at Maxar regarding the combination of this image technology, image processing technology from Vricon, and the vast image archive that Maxar and the capacity to collect new imagery that Maxar has. And the idea of this combination being this perfect combination of the technology and the inputs to build a really amazing product. I've been involved in remote sensing for elevation products for the last 20 years with LiDAR, SAR, photogrammetry. Really what we're offering with the Vricon product is one of these new cutting-edge technologies that's really not available from anyone else. So I want to take a little time first to explain the process a bit. As you can see on figure 1 on the left, what we're using is multi-view photogrammetry, meaning that instead of traditional stereo where maybe a pair or a tri-stereo flex might go over a target, we're utilizing multiple image views over a period of time. So as you can see there, we've got image stack dating from 2012 to 2020, utilizing the Maxar constellation, and all those green lines that you see in the image below are actually the rays of those image collects over the city of San Francisco. So you can see for building this model, that target has about 100 different images that are being used. And the real advantage of the multi-view photogrammetry is this idea that occlusion is nearly eliminated, because instead of having tall buildings that might be blocking the alleyways and streets between them, we're now looking down those alleyways and streets. So we're able to get pixels into these areas that previously, when we were correlating stereo images, we may not have had imagery. The second step of the process is taking all those images and correlating them together with a semi-global matching algorithms and machine learning. This is really the heavy compute piece of the Vricon process. When we're taking all these images and matching them, we're not just finding correlation points in the images and doing, like with traditional stereo, maybe you've got 5 correlation points that you can tie together, and you tie those 2 images together. Here we're talking about billions of correlation points because we're matching on a pixel-to-pixel basis. So for that entire image stack, we're correlating each pixel with the corresponding image pixel, and then the corresponding image and the corresponding image after that. So you end up with this very heavy compute process to tie all these pixels together. You also get some advantages out of that. First is the fidelity. Because we're matching on a pixel-to-pixel basis, you're able to replicate that input image fidelity. In this case, 50 centimeter fidelity. So you're getting these crisper representations of all your features in your 3D model build-outs because you're utilizing that pixel-by-pixel basis. Second piece that's really advantageous is the idea of accuracy without ground control points, like Isaac mentioned. Because we're matching each of these images together with the corresponding images, what they're actually doing is averaging out their native pointing errors. So with each of our satellite imagery, there may be a 5 to 10 meter offset on actual geolocation of that image just because of the native pointing error of the satellite. But when you combine multiple images together, you get a process that's called bundle block adjustment. And so by tying these images together, we're actually averaging out that error, getting the Gaussian distribution of the error and finding the ideal position on Earth for that 3D model to be constructed. So within a 3-meter CE and LE90, it's a 3-meter spherical error, or an SE90 is the accuracy we're able to achieve. So the output of those processes is the core Vricon 3D surface model product that you see in Figure 3. And this is a photorealistic, true textured 3D model where every pixel is actually located in its proper X, Y, and Z location. So we talk about the horizontal facades of buildings or steep terrain on mountainsides. Those pixels are not just image drapes onto a 3D surface. These are actual positioned image pixels. We choose the best image pixels from the stack and place them in the proper location. And then the final step is taking that core 3D surface model product and building multiple derivatives from the one core product. Now the big advantage of doing this is that we're able to, first of all, build this core 3D surface model at massive scale using AI and machine learning and vast processing power. We can build the core product over, as Isaac was pointing out, the entire surface of the Earth is the goal here. And then using that massively scaled product, we can derive these perfectly co-registered derivatives. So as you can see there, all the derivatives are going to have that same resolution and accuracy, the 50 centimeter resolution and the 3-meter absolute accuracy as an SE90. And these multiple derivatives all are perfectly co-registered to the 3D surface model and themselves. So I just want to take a little time here to walk through each one of these products. So as you can see, as these draw in, that perfect co-registration I was talking about. And this is really advantageous for multiple use cases, not just the idea that visually we're aligning, but when we talk about algorithms that may be extracting information from these different data layers, the idea that they are already aligned, and for the AI and machine learning applications to look at the data and not have to do matching from one layer to another to figure out, hey, this feature is actually this feature, I'm going to try and compare the two. It's already there. So it adds to that sort of efficiency in the workflows, as well as giving you confidence that what you're looking at and what you're extracting is going to match to any of the other layers that you compare it to. So the first layer, as I mentioned, is the 3D surface model. This is the core product that is built at massive scale by Vricon. And again, this is not an image drape on a 3D model. Every pixel in this 3D surface model is in its proper location. From that 3D surface model, one of the first derivatives that we want to derive is the automated classification. So this is an important derivative for building other derivatives down the line. And this classification process works by using not just the optical inputs of the 3D model, but we're looking at NVDI information, we're looking at height information. There's a bunch of different factors to produce automated classification of all the features that are represented in the 3D model. That classification layer can then be used to take the DSM, which is just a representation of the 3D model as elevation heights, and extract all those ground features that are either man-made structures or vegetation or any features that would interfere on a representation of the bald Earth. And so by using classification, we get a very good idea of where the ground is and where the structures that need to be removed are. Now with the DTM process with optical, when we talk about dense forested areas, we're not able to actually see through the trees. So we have to use very detailed classification to find ground patches within those forest canopies and around the edges of the forest canopies so we can understand how to interpolate across that forested area to get the best representation of the ground features. if we take the classification and combine it with the true ortho product, which is the nadir straight down view of the 3D model, we can extract building footprints from this. And by extracting building footprints and vegetation footprints, we can then build a 3D surface model, or a 3D vector model, excuse me, that represents all of those features that had been removed in the DSM DTM process as 3D vector features. So this is very different than the 3D surface model I showed you as the core product, because each one of these is an individual feature that can be attributed within a database. It can be queried against everything in a GIS type query environment. So utilizing the 3D vectors as individual features gives them a lot of value. And we've got market cases that I'll talk about where this has been very important to customers. So I'm going to dive into some of the real-world applications. Now, of course, I'm not going to cover everything that we're using this data for, but just some interesting applications that we've seen customers using the 3D surface, DSM, DTM, and vector products for. One of those is for disaster planning risk management applications, where by utilizing the 3D surface model, you're not only getting an understanding. In this case, we're looking at a storm surge inundation on a coastal area. Where's that water going to go? A terrain model could show you that. But by having a perfectly aligned optical reference, you're able to see, okay, what structures are actually being impacted by this? Are those access roads to those structures actually usable, or are they going to be inundated as well? We turn this model onto its side and look at it in a 3D perspective. Not only do we see the buildings that are being inundated, but to what floor those inundations might be happening. Are people going to be safe on the second floor, or are they also going to be in harm's way with that flood surge? Another application that we've gotten multiple customers for is this idea of line of sight viewshed analysis. Because of the high fidelity and accuracy of our data, where we're actually collecting not just the terrain at a high accuracy and high resolution, but all those features, in particular the vegetation features, because of the way that multi-view photogrammetry is able to use all those images from different perspectives of tree canopy, you get a much better representation of tree canopy than you would with, say, traditional stereo photogrammetry. So in this case, what we're looking at is a wireless broadband application where a wireless broadband provider is looking at a tower and trying to understand from that tower location what is the customer base that will get coverage with clear line of sight to their rooftop. We've also done projects like this for satellite broadcasting companies that are utilizing fixed satellite positions to understand the exact coverage of customers that they're going to be able to see and not see. Now, not only does this allow them to understand their customer base, but also in their marketing and promotion activities, they can understand how to target those activities so that they're getting just the clients that they may be able to transfer from a competitor to their services. The other important piece is truck rolls. The idea that if a customer wants to sign up to one of these services, but it's known ahead of time that there's a blockage in front of their property, the broadband company can either direct them to another technology or not send a truck out there and spend those monies to observe if it's a feasible area. We talk about propagation modeling. Radio frequency modeling for the telecom is a big market activity right now, especially as we're seeing the 5G networks starting to roll out. So these 5G networks are utilizing very high frequency spectrum. And this high frequency spectrum is very limited on how far it can travel because it's blocked by obstructions that may get in its way. So previously, where market evaluations for a telco radio design could be used with pretty low fidelity geodata because they were using lower frequency spectrum that could bend around obstacles and they didn't need as many antennas. It wasn't as important as it is today, where the geodata being used in the model planning process really has to be of highest fidelity and highest accuracy. because not only are these obstructions blocking more of the frequency, but because of the short distance of the travel of those frequencies, they're having to use a lot more antennas. And so in this RF planning process, really what it comes down to is a pre-plan of your market design, figuring out how many antennas can I use that is the least number of antennas to give me the best amount of coverage in a market. And then they'll deploy that plan, set up some test base stations in the area, do some drive testing, figure out how well the model corresponds to what the actual coverage is, and then come back and optimize that network. But that geodata is a critical component throughout that life cycle of those RF designs. And it's not just with standard RF designs. What we're starting to see now is that because of the complexities of 5G and these high frequency spectrum that they're using, we're starting to see more complex 3D radio planning happening, where in this case what we're looking at is an example of ray tracing, where a signal propagation is being bounced off multiple surfaces. Think of a pool table and your shot that's going to have to go off 3 bumpers before hitting the ball in. That's actually what's happening now with these signals, where in order for an antenna to hit a building that's maybe right next door to it, they're going to shoot it off a building that's 3 blocks away and have it bounce back to that building. So by having this very high accuracy and detailed 3D information, we're able to either utilize the 3D surface model in new advancements in radio planning or build these very high resolution 3D vector buildings that represent all these different height factors we can get in the 3D model. So as you can see here, we've got a building with several spires and a domed center, and being able to take that information that is contained in this high resolution 3D model and transfer it into high resolution 3D vectors is really where the future of the 3D telco planning as well as 3D or 2.5D building features is going. And I say 2.5D because true 3D would utilize sloped and pitched roofs. What we in the telco market are very interested in is the 2.5D application, where those slopes and features are represented as steps. We utilize a 2-meter step within our 3D vector products. You can see here, particularly for vegetation, that stepping is really critical in trying to get the most accuracy in the representation of the vectors that we can pull from the 3D model. So at the top is the actual 3D surface model, the core Vricon product, representing those trees with each pixel having a height for the tree canopy. We then can convert that into a stepped 3D model for vegetation, where you see every 2 meters, the trees are doing a sort of stepped contour to represent that shape. And then if that becomes too heavy of a data file for customers, we can also provide a traditional non-stepped tree representation. Still very accurate, but doesn't quite have the shape of the canopy in it. Another application that this 3D surface model and high accuracy, high resolution feature models can be used for is this idea of UAV flight planning. Understanding exactly what obstructions might be in a drone's flight path, avoiding those obstructions, finding the path of least risk for a drone flight plan, but also being able to see, in this case what we're seeing is from that flight position, what areas are visible to that UAV. Or vice versa, you could also utilize these 3D surface models to understand from a ground position or from a building who's able to see that vehicle and who's not. These 3D models could also be used for as far as like noise pollution. If we're talking about UAVs doing deliveries, how does the sound of the drone actually propagate through that city area? Or classifying all those features to the drone pilot based on elevation of your vehicle. What features are you in danger of hitting if you change course, and which ones will you be able to clear? These are all applications that this high resolution, high accuracy 3D can be used for. So with that, I'm going to pass it back to Isaac to talk more about not just the products themselves, but how these products in conjunction with applications and further Maxar improvements really have a future-looking roadmap. Isaac?
Thanks, Ryan. That was great. So as Ryan just suggested, this kind of next section of the presentation is really focused on some of what I think of are probably the most exciting and most compelling technology use cases that we have been working on and continue to focus on inside of Maxar. And the key to think about in the back of your head as I talk through this kind of next series of use cases is the power that data, high resolution 3D geospatial content, like what Ryan has just been talking through, the power that content can provide as you start thinking about integrating it deep into kind of the foundational data architectures across many different use cases. So for me, being an engineer by background, who spent a lot of time supporting defense and intel use cases in areas around the world, and really looking at the kind of critical problem sets associated with deriving information and understanding from diverse data sets being collected from different sensors on different platforms in the same environment at the same time. We've perpetually been in a situation where we struggle to integrate data, to bring data together. And really, this is a problem that is it's most acute in the context of our attempts to describe the world that we live in and to describe the world that we live in now, right? This whole concept of the fact that a lot of the questions that we in the community across many different markets and verticals, most of the questions we're most interested in relate to people in the world that we live in and activities that we, the people, are conducting, right? And that means a whole lot more than a foundational data set. It really comes down to that ability in today's world where we're oversaturated with remote sensing technologies and the ability to collect content, the ability to bring all that content together and enable humans and as well as machines to be able to integrate it, fuse it, exploit it, and generate insights, information, and intelligence from it. So what we're going to talk about now is a concept called georegistration. So let's see if I can get our slides to work. So Ryan was just talking about a use case centered around drone flight planning. And the reality is that most drones or unmanned aerial vehicles or even autonomous cars are packed full of sensors collecting data at various different times. And so above and beyond just the idea of being able to use foundational geospatial high-resolution 3D data to help plan and understand how to navigate your drone so that you don't hit things, a very base requirement. There's this other side of the coin where you're collecting a whole lot of information from these sources and it's critical information that tells you important details about the world. And oftentimes that information being collected from these what are now very small, inexpensive platforms packed full of sensors. A lot of that information can be some of the most timely, some of the most high resolution, most compelling data collected about a given scene, but frequently it comes with a whole lot of downsides. And those downsides can be in the fact either one, it's got a video camera on it where data is being collected as a video that has at best maybe a kind of metadata file that gives you GPS coordinates for where the sensor was at some point in time, but doesn't really tell you very much about where the images in that video are the planet, or what they correspond to. So what we have been working on for some time now, and this really came out of some interesting development looking at actually out of the early days of vision-based navigation development. So this was pre-GPS in Saib's portfolio. But what we've really been focusing on is this problem set of being able to automatically take data collected from different remote sensors and be able to very accurately register it against this pre-computed, high-quality, high-accuracy foundational data, and to be able to both update the metadata for that new imagery that's being collected, and then also fuse it together in real time. So we, a couple of years ago, at the GeoInt conference hosted by USGIF, we brought to market a product that we have titled Precision 3D Registration. And this is a pretty simple, lightweight software tool that is intended to be a general solution for automated georegistration of imagery. So I'm going to talk through a particular use case, but at a high level, this tool is intended to be very flexible. It's intended to be able to take imagery collected from many different types of imaging sensors, whether they be video sensors on low altitude drones, or whether it be huge satellite image strips collected by Maxar satellites or other third-party satellites, or anything in between, and be able to, in a completely automated way, take that image and register it against this foundation data, measure the differences between the original metadata that may have been included with that image and where the image actually belongs on the ground, and then provide updated telemetry and metadata that can then be fed into further downstream applications. So the real key here, and me coming out of the image processing world for over a decade now, that the idea of image-to-image registration has been a core topic that's been explored heavily in academia, also in the commercial marketplace, and also in many government programs. But we tend to find that the traditional 2D image-to-image-based registration solutions really struggle to perform when you have imagery that's collected at very oblique or off-nadir angles. And the real reason for that, the reason why those traditional algorithms struggle, is because the reality is that the world is three-dimensional. So when you start collecting imagery from oblique angles, you get a significant amount of what ends up being distortion in your image that's caused by the three-dimensional geometry of the features in the scene. So this means when you take a traditional ortho image as your reference and a heavily oblique image as the image you're trying to register, there's not a lot of similarity between the two, because that distortion ends up being a big component of the scene. So the real key here with P3DR is that rather than trying to register an image against a flat, nadir, orthorectified perspective of the Earth, instead we're taking this full, rich, three-dimensional model, and we're actually synthetically rendering a perspective image to use as the reference from the perspective of the source, the sensor that is collecting the new image. So this allows us to get a really high degree of similarity between the reference and the source. So what this means in practice is that even for the hardest georegistration problems, of which full motion video has for a long time been kind of the Cadillac problem, this means that we're able to create an algorithm that is robust and consistent and completely automated. So with the current deployed release of P3DR, we're able to take full motion video feeds, even from sensors with super long telescopic lenses, so tiny little soda straws pointing at the ground at high off-nadir angles. And we're able to automatically, in real time, register that data against the underlying 3D data and produce an accurate result that can either be fused in real time for visualization or can be populated into databases for additional analysis and exploitation downstream. So what you're looking at here on this slide, on this the top image that you see here on the right, that is an original image pulled straight out of a video feed with the original metadata as the sensor thought it was looking at the ground. And so you can see the fine red lines indicate the frustrum from the sensor. You can trace them back to where the sensor was flying in space. This was a small little UAS. Think of it as a commercial off-the-shelf DJI or something like that. And as your eye, so our eyes are extraordinarily good at pattern recognition. As you trace this out, you can immediately see that the roads don't line up. Even the scale of what's indicated in the image in the middle of this scene versus the underlying reference, the scales don't line up either. So as we look down at the image on the bottom, all of a sudden your eyes can immediately pick out that not only do all the roads line up, but the scale is correct, and the image, the new image coming from that video image, fits seamlessly into the 3D environment. And it's challenging to articulate just exactly how powerful this is in a static 2D image, but if we take another example and we start looking at kind of what this could mean in the context of a mapping environment, here you start to see the power, right? So again, if we look at the top left, you can see the foundational 3D data. If you look at the top right, here we've taken a vector network, a vector road network out of a database and overlaid it into that reference. So imagine that you've extracted a road network with all sorts of attributes and characteristics, valuable map data. You can overlay it inside of your kind of foundational environment, and you get to appreciate the value of those two data sets together. But if you take your real-time view of the world, your situational awareness, your best perspective of what's happening in the world right now, particularly if you're looking at dynamic things in the scene. If you look at the bottom left, if you take that new image collect with the original metadata, that misalignment makes this scene completely unusable. The fact that the new image doesn't line up with the foundation and it doesn't line up with the map data that you have injected into the scene just makes it a mess. Your brain can't figure out what's going on. But in the bottom right here, all of a sudden you have a scene where you have accurate foundational data with map content, authoritative map content coming out of your GIS catalog, and your real-time information about exactly what's happening in that scene right now with the latest dynamic content in that scene also represented. You have all those scenes tightly integrated into one scene where you, the user or the analyst, can exploit them all together. You get that full perspective with the added value from each of those different data sets that comes out of that perfect correlation together. So this capability, as I mentioned kind of from the beginning, we've designed it to be very flexible. So what I was showing you before is a purely kind of 2D to 3D registration use case where we're taking a new flat image collect from a remotely sent sensor and we're registering it against that underlying 3D scene. And the 3D is providing the accuracy because we have that full rich definition of the world that is being collected. But this also enables us to start looking at 3D to 3D registration. This is becoming increasingly an important value add in the marketplace where we see new organizations coming up with use cases for being able to go out and do tactical kind of individual collects with small, lightweight commercial drones collecting ultra high resolution imagery of, say, a construction site or you name it use case. And being able to rapidly process that new imagery into these super high resolution 3D models that may or may not be well referenced into the kind of global coordinate system that that we use to describe the actual planet. So the fact that we can support 3D to 3D registration means that all of a sudden you can take all of the individual small scale but ultra high resolution collects that you're doing, and you can automatically register them into a common datum, a common reference frame. You can leverage the absolute accuracy of that underlying satellite-controlled foundation data as a means to kind of pull that whole picture together, right? So I think now we can take one more attempt at a video. This one's a little bit shorter, so hopefully the platform will be able to handle it. But just to demonstrate what that means, and again, I mentioned that showing this capability in 2 dimensions is a bit challenging. So if we look at it in 3 dimensions or in a video form, we'll see whether the platform's going to be nice to us now. But it helps you to appreciate exactly what I'm talking about. So this video is going to showcase an example where we have taken a new collection that was actually performed by a partner of ours and processed. The new collection was collected from a small commercial off-the-shelf low altitude drone flying a kind of standard commercial off-the-shelf imaging sensor. And that data was taken by the user, processed into a new 3-dimensional, well, in this case, so to start off with, the sensor is collecting in real time, collecting video of the scene. And so I'm actually going to back up for a second since I can, just so we can see. So what we have here, so on the left-hand side, you're seeing the raw image collection from the sensor itself. And on the right-hand side, again, you're seeing the way that that video is projected into the scene based on the metadata coming from the sensor. The alignment is quite poor. You can see that immediately by tracing out the roads in the video versus the roads in the accurate foundational reference data. So what we're going to see next is that exact same video being registered in real time against that foundation data, having the metadata updated, and then being fused on top. So what you're seeing right now, you see that car moving, that dynamic content in the scene moving, and you see it tightly registered into that underlying scene to a point where I can actually measure anything out of that video. And I'm measuring based on the accuracy coming from that controlled satellite-derived foundation with the real-time context coming from that, that new collect in the video. These are similar examples. This one's actually from the perspective of the sensor itself, where you can see the red box is where it thinks it's pointing. Now the image is placed where it really belongs. But the point to take away from all of this is that all of this data is extremely useful. It has traditionally not been terribly well represented as a geospatial data source. So video in particular has lived in its own silo as a data source that is only really good for watching in a video player. But the reality is it's just a string of images that are all mapped together. And using a tool like P3DR enables customers and clients and users to really be able to make the best out of that content and to really be able to bring it in and provide an augmentation to their larger kind of map databases and provide that additional context that the kind of new image collector, that real-time component, can uniquely bring. The other kind of added piece to that, and this is one of those really exciting ones that I'm only just going to touch on, it's probably worth an entire other webinar to talk about, is the fact that all that math that we're doing inside of that Precision 3D registration tool, all that math is the math not only to determine where that sensor is pointing on the ground, to take that image and figure out where it belongs on the ground, but in order to do that, we actually have to calculate exactly where that sensor is in space, in 3 dimensions. So I mentioned early on that one of the original driving reasons for the development of this technology came out of the world of navigation, and particularly GPS-denied navigation. So this is one where we're actually working with a number of partners to pilot implementation of this same software on board actual platforms to support vision-based navigation use cases. So either GPS independent or as an augmentation to GPS for a navigational solution, which is kind of a really key unlock as we start thinking about this future that is kind of saturated with autonomous and unmanned vehicles, or vehicles where we have a high density of kind of interaction between these different platforms that are competing for airspace and space on the ground too. So with that, I'm going to switch gears really fast, and I know we've run a little bit long with everything going on, so I'm going to hit this really kind of crisply to bring everything back around. But one of the key things I really wanted to talk about and that I'm most excited about in this world where Vricon has now become Maxar, where we've joined the Maxar fold officially, is looking forward into Maxar's larger roadmap, and particularly their roadmap around their Legion constellation. So we've been operating for 5 years, pulling as much imagery as we possibly can out of the commercial archive from all of the sensors that have been collecting to date. So many of you are familiar with everything up through WorldView 3 and even WorldView 4 before we lost it last year, the year before. And right now that archive sits at something like 110 petabytes, which is awesome for an image processing nerd like myself. But coming up in 2021, Maxar is really taking the next huge step forward in this commercial collection capability by launching what they're calling WorldView Legion. So WorldView Legion is going to be this capability. It's going to be initially it's going to be 6 high-performing satellites that are all going to be collecting in different orbits around the Earth, which, I mean, to sum it all up, it means a heck of a lot more collection, a whole lot more capacity for 30-centimeter collection, which is one of the key places where Maxar has really been unique in the market, and the quality of that content not only is just amazing to begin with, but it enhances the quality of the 3D product we're able to generate. Then we're able to start looking at kind of response times as well, right? If we put this in a different context, these 6 new satellites collecting at more or less 30-centimeter resolution with super high accuracy and all of the spectral bands of the WorldView class means that we, from the 3D perspective, have a ton more content to start working with. And we can start thinking about scenarios where this constellation can be tasked to look at specific places on the Earth on a regular basis, multiple times a day, to allow us to build kind of this persistent assessment of the Earth that we live in, the world that we live in, and be able to actually watch changes unfold in 3D as we move forward, which is a huge, huge potential unlock for, I think, for the whole community in general. This ability to collect that much content, to almost double the total capacity, going from 3.7 million square kilometers up to 6 million square kilometers a day of the highest resolution, most accurate commercial satellite content that's available on the market, is going to be an entire game changer. And what it means for the globe in 3D is it means we get to build faster. It means we get to continue to improve even upon our already industry-leading accuracy from a foundational perspective. And it means that we get to continue to power up those applications built on top of the globe in 3D to do things that just haven't been able to be accomplished in the industry before. So with that, I think I have used up almost all of our time. So Abby, I'll hand it back to you for just a quick second.
Yes, we are out of time. So Dacian has been in the chat trying to very quickly answer everybody's questions, so we're out of time. Ryan or Isaac, do you guys have any closing sentiments?
I'll jump in for just a second and say that we really appreciate everyone who had a chance to log on today. As Abby mentioned, we'll send out a recording of this webinar, and we'll try to follow up with answers to the questions as best we can. But I have a feeling that we will probably be doing another version of this or a continuation of this sometime soon, so please be on the lookout for that. We'll, there's a lot to the story that we're eager to tell, so we appreciate you joining today.